Okay, let's work a few of the multiple regression problems. I've got 3 problems here for you. I know that's not a lot. I know you guys want more problems, but I think in general you're going to find that this is pretty easy stuff. I'm pretty limited on what I can ask you. So let's take a look here. All right. Okay, the production manager of High Point Sofa and Chair, a large furniture manufacturer located in North Carolina, is studying the job performance ratings of a sample of 15 electrical repairmen employed by the company. An aptitude test is required by human resources to become an electrical repairman. The production manager was able to get the score for each repairman in the sample. In addition, he determined which of the repairmen were union members and which were not. The sample information is in Minitab. All right, so we want to use backward, although I think, hold on. Yep. All right, so let's see here. Let's go into JASP. We've got our data here in JASP. We want to go into linear regression. All right, so what do we want? We want to predict, all right, we want to predict their performance. All right, so here, predict job performance. So performance is going to go in our dependent variable. And then according to our data, we have X's of aptitude and union. All right, so what do you guys think about that? Are we going to put aptitude and union in? Hopefully you're saying, oh, Angie, we got a problem. So we are actually only going to put aptitude in. Why? Because union is a categorical variable. Even though it's coded as 0, 1, a 1 stands for in a union, okay? All right, so we can go to backward elimination. All right, this is just practicing, even though it doesn't really make sense with our one variable in there. We go under options and change that removal to 0.05. All right, we want to go into statistics, check collinearity diagnostics, and then we want to go under plots and check residuals versus predicted and the QQ standardized residuals. All right, so let's take a look at what we've got here. All right, so the first thing we want to do is write our final equation. All right, so write our final equation. How are we going to do that? We're going to go to our coefficients table. We see that aptitude is significant with this p-value of 0.038, so it's in the model. We see our unstandardized coefficient, and we see our intercept. So job performance, y, equals 43.546, our constant or intercept, plus 4.594 times aptitude. All right. Using the results of the multiple regression, interpret the adjusted multiple coefficient of determination. So here's our adjusted R squared. So we've got 23.5% of the total variation in job performance is explained by the aptitude test. Okay, are all assumptions met? All right, so let's start with multicollinearity. All right, so we see that our VIF is less than 10. All right, so that's met on aptitude. Scroll down to our QQ plot. So this is one where it's a little, we really don't like to see this deviation from our diagonal, but otherwise it looks really good. So most likely, I'm guessing, is that this right here is just an outlier residual because everything else is really close to our line. So I'm going to say, QQ plot looks like residuals are close to normal. All right. And then lastly, we want to look at our residuals versus predicted. Does it look like random scatter? Yeah, we don't see any kind of trend. We don't see a positive trend or a negative trend or a nonlinear trend. So I'm going to say residual versus predicted plot looks like random scatter. Okay? All right, next problem. A real estate developer wishes to study the relationship between the size of a home a client will purchase and other variables. Possible independent variables include the family income, family size, whether there's a senior adult parent living with the family, and the total year's education beyond high school for the husband and wife. And this should say JASP. All right, the sample information's in JASP. All right, so we want to use backward elimination here. All right, so we are looking for, all right, size of the house. All right, so let's go into our linear regression. All right, so looks like here's our information. We've got family, square feet, income, size, senior, and education. So we want to predict the square footage of the house. All right, from income, size. We can't include senior because it is qualitative. Education. I'm wondering, family income. Let's see here. We got everything. Income, size. Yep, that's everything. Because I was thinking that family is just a name for the actual family. So that's everything. We want to change our method to backward. We want to go under statistics, check collinearity. Go under options, change our removal to 0.05. And under plots, check residuals versus predicted in the QQ plot. All right, so what do we have? Looks like we ran 3 iterations. All right, and so notice here we start with income, size, education. Education having a large p-value gets dropped. We go to income and size. Income has a large p-value, so it gets dropped. And so we're left with just size of the family in the model. So does it make sense that size of the family predicts the size of the house? And yes, of course, right? That makes total sense. All right, so our equation here would be y equals, all right, we've got our final intercept in our third iteration, which is 1271.586. So that would be the square footage of a home with a size family of 0, all right, plus 540.69 times size. So basically for each additional member of a family, we need about 550 more square feet. All right, let's interpret our coefficient of determination. So we go up here to our model summary, and we're looking at our third iteration of adjusted R squared. So we see 80.2% of the total variation in house square footage is explained by size of the family. All right, are all assumptions met? All right, so let's go back down to size, and we see that our VIF for size is clearly less than 10. All right, let's go down to our QQ plot. QQ plot implies residuals are normal. We see that our dots are all right along our diagonal here. And then our residuals versus predicted plot shows random scatter again, right? Just throwing some dots up there. So it looks like our assumptions are met. All right, last question here. The Bank of New England is a large financial institution serving the New England states as well as New York and New Jersey. The mortgage department of the Bank of New England is studying data from recent loans. Of particular interest is how such factors as the value of the home being purchased, education level of the head of household, age of the head of household, current monthly mortgage payment, and gender of the head of household relate to the family income. The mortgage department would like to know whether these variables are effective predictors of family income. All right, so we want to predict family income. All right, so this is going to be our first set of variables here. So we want to predict income from value, education, age, mortgage, and maybe gender. Be thinking about that. All right, so we're going to put income in our dependent variables. We want value, education, age, mortgage. What do you think about gender? Is gender going to go in? And hopefully you're thinking, oh, wait, that's qualitative, right? Because here a 1 is going to stand for male or female. So since that's qualitative, we're only going to look at value, education, age, and mortgage. And we're going to change our method to backward. Under statistics, we check collinearity diagnostics. Under options, we change our removal to 0.05. And under plots, we check residuals versus predicted and QQ residuals. Okay, so again, it looks like we ran 3 iterations. We started with value, education, age, and mortgage. Mortgage had the largest p-value, so it was removed. Then we ran value, education, age. Age had the largest p-value, so it was removed, leaving only value of the home and education of the head of household. All right, so what does that mean? It means that y equals, and we're looking only at our third iteration here in the coefficients table, 72.963 plus 0.070 times value plus 1.125 times education. All right. And again, notice here, just because the unstandardized numbers, it appears as though value may not mean a lot. We don't know the units of the value, so it appears here it's in thousands of dollars, so the slope's going to be really small. And if we look at standardized, we see by the magnitude of the standardized values that value actually contributes a whole lot to this regression equation. All right, let's interpret our adjusted R-squared. So we scroll up to model summary, look at our third iteration, and we see 56.9% of the total variation in income is explained by value of the home and education of the head of household. All right, are all assumptions met? All right, if we go down to value and education, we see that they both have a VIF of 1.021, so we've got our VIF is less than 10. Scroll down to our QQ plot. That looks perfect, guys. That's about as good as we can ever see. So the QQ plot says residuals are normal. And then our residuals versus predicted is again random scatter. So again, all of our assumptions are met. All right, so hopefully this helps clear up how to do multiple regression in JASP.